let U again be an open set, and let f be a function on U, we say that f is holomorphic on the set U if it is complex differentiable at every point of U, and we assume that f prime, so the complex derivative at each point, is also continuous. So this is a very important class of functions for complex analysis. It's basically the class of functions that we study. First, let me remark, we'll see later that continuity of f prime is not really needed in this definition. It comes for free from complex differentiability, but that takes some work to show, and assuming continuity of f prime makes certain arguments easier in the beginning. Okay, so here are the usual calculus rules for derivatives. These hold for complex derivatives just as well. And I don't want to belabor it, but you have the sum rule, the product rule, the quotient rule, the chain rule, the derivative of a constant. The complex derivative of a constant is identically 0. The complex derivative of just the function z is identically 1. And then using the rules above, you can take the complex derivative of any monomial, certainly. You would just use the product rule to show that. And we get out of this, and I should say that all these rules can be established basically in the same way that you would prove them for one-variable derivatives in a calculus course. There's nothing drastically different. We get that polynomials with respect to the complex variable z are holomorphic in all of C, and the derivative has the usual derivative rule. So p1 plus 2p2z all the way down to n pn z to the n minus 1. And also you get directly from this that rational functions in the complex variable z are holomorphic on the set of the complex plane minus the zeros of Q. So here P and Q would have to be polynomials, obviously. Okay, and the next thing worth talking about is a more general chain rule than what we have here. So here, this is supposed to be, I'm composing two holomorphic functions or two functions with complex derivatives, and you get this type of chain rule. But what we'll talk about on the next slide is that you can have f with a complex derivative and g just with kind of a traditional calculus derivative, and the same type of formula holds. So here is what we'll call a more general chain rule. So assume that little f is complex differentiable at whatever point we're studying, and assume gamma is just a differentiable map from an interval into the domain of f. This more general chain rule says that, well, we can view f of gamma of t as a function of t. So this would be just the composition, and it would go from AB into C, and we could view this as a vector-valued function of the real variable t. And you can show that the derivative of this with respect to t is this product. And here we should emphasize that this is the complex derivative of f, while this is a more traditional derivative. And so here you could think of gamma as basically a vector-valued function. Maybe you would write it as x of t plus I y of t, and gamma prime of t would just mean take one variable derivatives of each component. Now let me give a sketch of how you prove this. to do all the epsilons and deltas may be a little too much in a short video, but I think with little o notation you can kind of sketch how it goes pretty easily. So we want to show that this composition function is differentiable at some point t naught, and we want to show that this is its derivative. And so the way we show that is with this, we attempt to show that the expression here is little o of t minus t naught. And so we'll break it up into pieces where we have f of gamma of t minus f of gamma of t naught, and then this part resembles the definition of the complex derivative. And then we also have another part where we have the derivative of f, and a section that resembles how you define the real variable derivative of gamma. Okay, so the first part, you could say, if we're cheating a little, this is sort of like little o of gamma of t minus gamma of t naught. So technically it would be little o of something like z minus z naught, but you can make sense of it in this way if you dug in a little more carefully. And then this second part, since gamma is differentiable, is little o of t minus t naught, and then having this constant in front is not going to change the little o condition. And okay, so this part is a little o of this expression. I confess this is the sketchy part. The inside is gamma of t minus gamma of t naught, and since gamma is also continuous at the point, I guess since it's differentiable, this difference will be big O of t minus t naught. And so we have something that's little o of big O of t minus t naught. That'll still be little o of t minus t naught. And if you add the same type of error term, it doesn't change it. So it's still little o of t minus t naught. So that's just a sketch of how you would show that f of gamma of t's derivative at t naught is what we claimed it was. And so again, this is for f that's complex differentiable, and gamma that's sort of a vector valued function of one real variable t, and you take a derivative of each component. Okay, this more general chain rule is surprisingly useful just in these special cases. So if I have f complex differentiable at the points in question, then I look at f of x plus iy, and I can view temporarily x maps to x plus iy as my function, where y is fixed. And that's the same as taking a partial derivative of this with respect to x. I'll get the derivative of f, the complex derivative, times the derivative of the inside with respect to x in each component, and so this will just give me a 1. On the other hand, if I take dy with respect to f of x plus iy, now thinking of this as the map y goes to x plus iy, well, I'll have the complex derivative with this plugged in, but then I'll take the derivative of x plus iy in each component with respect to y, and you'll just get I out of this. So you get I there. So here's just another way to write that. If f is broken up into its real and imaginary parts, what this says is that we took the partial of f with respect to x, so you could view that as taking the partial with respect to x of the real part and the imaginary part separately, and the above computation showed that that was always equal to the complex derivative. On the other hand, the partial with respect to y, if we correct this I term by multiplying by minus I, we get that f prime is also equal to these partials with respect to y. So this is taking df dy would really be uy plus I vy, and we've multiplied it by minus I to get negative plus vy minus I uy. Okay, and this simple observation gives us the following result. If f is complex differentiable at a point, and we break it up into its real and imaginary parts, then the real and imaginary parts have to satisfy this equation. And that's just looking back over here, matching the real and imaginary parts of the complex derivative. So you get ux is vy, and uy is negative vx. So these are the Cauchy-Riemann equations, and we'll have another way to interpret these later. For now, we can use the Cauchy-Riemann equations to prove that certain functions are not complex differentiable, and you can also use them to prove some fundamental properties of holomorphic functions.